Wanted to work through the worksheet on the two-slit experiment and interference of light. So in this worksheet, we're told that we have an arrangement that consists of two narrow slits. We're told that we direct green light onto the two slits. The wavelength of the green light is 514 nanometers. We're told that the two narrow slits are separated by 0.05 millimeters, and we're told that 2 meters away is a screen on which we observe the interference pattern of the light that emerges through the two slits. So the question asks us, or the worksheet asks us, to sketch out the situation and annotate the sketch. It asks us to think about the second dark fringe away from the bright central maximum, and to figure out the angle of the second dark fringe from the central maximum and the position on the screen of this second dark fringe from the central maximum. And then it asks us some questions about what if we did this, or what if we did that? What if we changed the wavelength? What if we changed the slit separation, etc., etc. So let's work through these parts. So first part, create a sketch of the double slit experiment and annotate that sketch with the information that you're given. So here's my sketch. The slit separation is 0.05 millimeters, or that would be 5 times 10 to the minus 5 meters. So I'll indicate that over here on the left-hand side. The separation between the slit arrangement on the left and the screen on the right is 2.0 meters. So I'll indicate that. The wavelength of the light, the green light that we're shining on the two slits on the left and creating the diffraction pattern on the screen on the right, that's 514 nanometers. And as a result of that, we get a diffraction pattern on the screen on the right-hand side from the light that's been shone on the two. It's going to look something like this. So in the center, I'm trying to indicate with the red line the bright central maximum. Above and below the center, here for example, below, here for example above, and further below and further above are other bright maxima, bright fringes. And then between the central bright maximum and the neighboring bright maxima is the first dark fringe. Between those neighboring bright fringes and the next neighboring bright fringes, right at the top and right at the bottom, is the second dark. This is the dark fringe that we're asked to consider in the numerical part of the problem. So I'm going to indicate its angle with a theta 1. I'm going to indicate its position with a y1. The subscript 1 is the order of the dark fringe. In two-slit experiment, the dark fringe orders count from 0, count 0, 1, 2, 3. The nearest one to the central maximum is the 0th order dark fringe. The next one, which is what we're talking about, the second one, which is what we're talking about, is actually the first order dark fringe. So let's calculate the angle of this particular dark fringe. The master equation for the angle is this equation here for the location of the dark fringes. In this equation, lambda is the wavelength of the light, d is the separation between the slits. theta is the angle of the dark fringe, and m is the order of the dark fringe. So m would count 0, 1, 2. As I mentioned, we're interested in the second dark fringe from the central maximum, which is order m equals 1. So I'm going to rearrange this equation. I'm going to rearrange this equation for sine theta, for theta. So I'm going to divide through by d. I'm going to fill in m equals 1. And I'm going to take the inverse sine. So if I do all those three things, this is the inverse sine to get the angle. Here's the argument of the inverse sine. We've got the wavelength divided by the slit separation, because I divided the equation through by the slit separation. We've got a factor of 3/2 because I filled in the order of m equals 1. And all these numbers, the wavelength, the separation of the slits, I can fill these numbers in. I won't write them out. When I did the calculation, I got 0.088 degrees for the angle. What about in part 3, the position of the slit on the screen? So that's this coordinate y. Well, there's another master equation in terms of the position on the screen. Let me write that out. It's this equation here. Y is the wavelength of the light again. D is the slit separation again. But now in place of sine theta, we got the distance to the screen. That's the L in the denominator. We got the position on the screen. That's the y in the numerator. This equation, unlike the previous equation, is approximate. It's a good approximation when y is small compared to L. So it's based on what's called the small angle approximation. Again, here, m in general is an integer, 0, 1, 2, but we're thinking about the m equals 1, the second dark fringe from the central maximum. And so I'm going to rearrange this equation again. This time I'm going to rearrange it for y, the position. I'm going to rearrange it by multiplying by L, by dividing by D, by substituting in m equals 1. If I do all of those three things, I'm going to get 3L lambda over 2D. Again, I got the equation by dividing by D. So I get D in the denominator on the right here. Multiplying by L, I get L in the numerator on the right. Plugging in the order m equals 1, so I get this factor of 3/2 from the quantity in parentheses here. And again, if I substitute in on the numbers, I won't do that. I got 3.08 centimeters. There's one final part of the question in which we're asked to imagine changing the wavelength of the light, changing the spacing of the slits, changing the distance to the screen. And as we change those things, think about how the location of this dark fringe on the screen will change. So to solve this part of the problem, I'm going to write down again the equation that we had figured out for the location of the m equals 1 dark fringe on the screen. It was this equation here, 3 times the distance to the screen times the wavelength of the light divided by 2 times the slit separation. So let's then go through, with this equation in mind, these 4 different operations in which we change the setup. So the first one says, let's replace the green light with orange light. Now what we have to know here is that orange light's wavelength is longer than green light's wavelength. So we're increasing the wavelength. If we increase the wavelength, Then, if you look at this equation, with the slit separation unchanged, with the screen distance unchanged, we're going to increase the distance to the dark fringe from the central maximum. And so we'll increase that distance. Second part of this question, we're going to replace the green light this time with violet light. Violet light has a wavelength that is less than green light, shorter than green light. And so we're decreasing the wavelength. Again, if this distance to the screen is unchanged, the slit separation is unchanged, but we've decreased the wavelength, we're going to decrease the distance to the dark fringe, the m=1 dark fringe. The third part of the problem, we're going to change the spacing between the slits. We're going to increase the spacing between the slits. So D is going to go up. If we increase D, because it's in the numerator, then we're going to decrease Y. We'll correspondingly decrease Y. So the distance to the second dark fringe, or the m=1 dark fringe, is going to decrease. And then finally, we change the distance between the slits and the screen. We decrease that distance. So L is going to go down. If we decrease the distance to the screen, then look, L's in the numerator. So that means that we'll correspondingly decrease the position of the dark fringe on the screen. Anyway, that was an example of the two-slit experiment. It's a famous example of interference of light. It was the experiment, laboratory experiment, that demonstrated that light has wave-like properties. And we worked our way through understanding the two-slit experiment, the angles of the fringes, dark fringes, bright fringes, the locations on the screen of the dark fringes and bright fringes. And we've also talked about the dependence of the positions of the fringes on the wavelength of the light, the separation between the slits, the distance to the screen.